Swayam Prabha. Digital India. Educated India.
Hello everyone. In the last class we looked at the linear convection equation and we applied our discretization schemes FTFS, FTBS and FTCS, and we saw that for the positive convection speed your FTBS is the correct scheme which gives you the desired result. Of course, you need to make sure that your Courant number lambda is less than 1. That means your C delta T, the information that is traveling with the convection speed is not jumping over the grids. Okay. And we saw that if you use the central differentiation scheme, then it gives you basically oscillations and it will eventually blow up. And if you use a basically negative convection speed, then you have to basically switch to the FTFS because the information is now traveling from right to left. Okay. So, we have to always honor the upwinding. Okay. Both are called upwinding. So, upwinding is decided by the direction of your convection. So, we looked at this linear convection in the last class. So, now we want to see what happens when we have a non-linear convection. That means del u by del t plus u del u by del x equal to 0. So, as we discussed in the last class, if it has got two solutions and if you add both the solutions, that will not obey this equation, and that is why it is not a linear equation. Okay. And this makes the things more complicated. Okay. You can in fact write this equation in the conservative form, that will be del by del x u square by 2. That also tells that this equation is non-linear. Okay. So, let us use the same logic, the same approach that we had for the linear convection and try solving these equations. Of course, there will be one difficulty here in estimating your Courant number. So, earlier the Courant number we had was C delta T by del x, right. When it is non-linear, your convection speed itself is unknown. Okay. That is also a part of the solution, right. So, you do not know a priori what is the value of u delta T by del x. Okay. So, that makes the things little bit complicated, okay, because your u itself is unknown. The other thing is that u is changing, okay, everywhere in the grid. Okay. Wherever you have higher u, okay, you can have regions where the speed is high, the regions where speed is low. Okay. So, accordingly your Courant number will also change. Okay. So, that makes the thing little bit complicated. Okay. So, using the same approach, so now instead of C you have this u y n, okay, appearing on the right hand side. This is still the FTBS, okay, and we are okay, and we are using the same form of the initial condition. Okay, this is 0.5 to 1 and this is square wave, okay, which is traveling. Okay, and this is the pseudo code. Okay, you can write in MATLAB or Python or Julia or any favorite software that you are comfortable with. You can in fact write in Fortran or C also. It is a very simple problem. Okay. So, the only change that we have from the linear convection is this term. Okay. So, you are solving for u, you are using the u1, the older u value here, and this value gets updated every time. Okay. You can see that u1 equal to u. So, u1 is getting updated every time, okay, and this is the solution that you are getting. Okay. So, once you solve it, okay, it is a very coarse grid. Okay. So, your x max is still 2 and n max or n equal to basically n x is equal to 51. Okay. That gives you the dx is equal to 0.04, okay, and your t max is basically 0.5 and nt, if I am not wrong, it is around 151. Okay. And that gives your dt as equal to 0.0033. So, as I told you, you cannot determine a priori the CFL number, but still you have to obey that condition that the CFL number should be less than 1. Basically, we are not jumping over the grids. Okay. So, this in this particular case our delta t is sufficiently small. Okay. So, you can see that our solution now is travelling on the right as we expect, but there is another important thing that you must notice, which was not there in the case of your simple linear convection. So, what is happening here? You can see on the right hand side. So, this gradient is becoming sharper and sharper if you look at the right hand side. So, if you look at in the right hand side, this is becoming sharper and sharper. So, of course, it is not maintaining the shape, that is because of the numerical diffusion and our grid is very coarse. Okay. But the other thing that you notice that you can see the difference in the gradient here and the gradient here. Okay. So, this is becoming more and more as it moves right, it is becoming more and more steep. Okay. So, this is called non-linear steepening. Okay. And that is happening because of the non-linearity in the problem. Okay. If it were a linear problem, then you would not see this steepening happening. Okay. And this steepening ultimately leads to the formation of shock. Okay. So, the equation that we have del u by del t plus u del u by del x equal to 0 does not give you the smooth solution and it can lead to a shock. Okay. On the other hand, if you have a elliptic problem, that gives you the smooth solution. We have also discussed that in the class where we were talking about the characteristic of the PDEs. Okay. So, this you can see that this will become more and more straight, okay, and ultimately the shock will develop, okay, due to the nonlinear steepening. So, that is a very important observation. Okay. You can see the same thing here. So, here what I have done, I have taken higher dt compared to the last one. Okay. So, I have just double the dt size, okay, and you can see that now it is basically you can see that it has moved faster on the right hand side, okay, because dt is higher. Now, what is happening here? Okay. So, here I have refined the grid a lot. Okay. So, earlier it was 0.0004 and now I have made it 0.0066. Okay. So, I have refined that, I have reduced the dx, okay, but kept the dt as same, okay, 0.0033. Okay. So, what is happening that although we do not know the value of the CFL number, it is basically disobeying the CFL condition or the Courant number condition. That means, your dt by dx is basically becoming greater than 1, or more precisely u dt by dx is becoming greater than 1. Okay. And that is why it is basically you can see that you are not getting the solutions that you want, and it is basically showing you some kind of shock which is basically getting developed here. Okay. So, that is unphysical and that is happening because we are not obeying the Courant condition, Courant number condition or CFL condition. Okay. If you are decreasing the dx size, you have to accordingly decrease the dt size also. Okay. And typically in a CFD solution, because it is a complex problem, you do not know the dt value. So, what you need to do is every time you have to calculate local delta t, okay, the local Courant number, and so your grid may be non-regular and non-uniform. So, your delta x may be different everywhere, your u may be different everywhere. Okay, let us say here big, here small, here very small. So, delta x is different, delta your u is different, okay, but you have to make sure your lambda is less than 1, right. So, you based on the lambda, so lambda is equal to u delta t by del x, you know from your previous iteration, okay, you know the value of delta x. So, you calculate the delta t local at every cell, okay. You have calculated and then you basically look at the entire grid, okay, at every delta t and see what is the minimum of this local, okay, and that will become your delta t global. Okay. So, use the delta t everywhere and march with that delta t, and this you need to do at every time step. Okay. Because we even if one cell is if you are not using the minimum value, maybe there are 1 or 2 cells where C delta t or U delta t is basically greater than delta x, that means it will jump over the cell and it will not give you the correct solution, or it will blow up. Okay. Or what you do in some cases, you want to have basically the solution at finite time steps, right. So, what you need is that you are not fixing the CFL. Okay. So, here you can fix, let us say lambda equal to, you fix as 0.5, and then based on that you calculate delta t everywhere, right. But the delta t is changing in every time step. The other way is that choose a sufficiently small delta t. Let us say if I had taken here dt equal to 0.00033, which is basically 1/10 of the time step that has taken, right. It will be slow, but it will not blow up, okay, and it will give you the correct solution, right. So, that is basically fixing the time step. So, here we are fixing the CFL number, and the other case is the fixing the time step. That means you are not changing at time. So, your delta t is a small quantity, maybe much smaller than delta t local minimum, okay, and but this is fixed. So, what is the advantage of fixing time step? Let us say that you are interested in certain frequency in the flow, okay, you are, let us say you are simulating flow past a cylinder, okay. So, there is a flow past a cylinder, okay, and you are having the vortex settings, okay, and you want to find out at what frequencies the vortices are generated, right. So, what you will do? You will put a probe here, for example, let us say, okay, at this x point, and you will measure your signal, okay, that is what you are measuring. So, this is your time, and let us say your velocity, okay. And if you want to find out the frequency at which the vortex change is happening, what you will do, you will basically just do an FFT, the fast Fourier transform of this signal, and it will give you the frequency, or you can just measure also. If the delta t is fixed, delta t is not changing, then you can use this. If the delta t is changing, then you cannot use the FFT, right, because your delta t itself is not fixed. Okay. So, the 1 by delta t which gives you the frequency is basically not fixed, right, because delta t is changing in every time step, right. So, if you are interested in basically getting the frequency information, you would need to use a fixed time step rather than fixing the CFL number. This is typically very useful if you are doing LES and DNS. Okay, in the RANs, you are, or your only interest is basically to get the mean flow. Okay, we will go into the detailed discussion of RANs and LES in the later classes, but I am sure if you are taking this course, you might have heard this term RANs, which is the Reynolds average Navier-Stokes, and LES and DNS, which are basically large eddy simulation and the direct numerical simulation respectively. So, in the RANs, you are only interested what is happening at the basically steady state time step, right. So, that means your del by del t term in the Navier-Stokes is going towards 0. In that case, does not matter what your CFL number you are using. Ultimately, as long as you go to the final solution, which is your average solution, you are happy with that. Okay. So, in fact, in those cases, we use implicit time stepping for RANs. In that, your boundation on the CFL number is not necessary. Like we are seeing that the lambda should be less than 1, that is not necessary. You can jump over the cell, okay, and as long as you are getting convergence and your del by del t term is going to 0, it should be fine. Okay. So, you are not worrying about what is happening in the intermediate steps. Okay. That is what it means. Okay. So, this was the nonlinear convection. Now, let us go to the diffusion equation. So, as we discussed, the diffusion equation is del u by del t plus equal to nu del t by del x square, okay, and this is parabolic in time and elliptic in space, okay, and here in this case we will use this FTCS, okay, forward in time and center in space. Why we are able to use FTCS here, but not in the case of convection? The reason for that is, you know, from your experience is that what is the role of diffusion? It basically diffuses, it basically dissipates. It has no directionality, it does not have a wave traveling or propagating in a certain direction. So, if you have something, let us say like this, it will with time, if you have a diffusion, it will start dissipating like this, and then it will become like this. So, it will start dissipating, right. That is what the mean of the diffusion, right. So, it does not have the directionality. So, you can use the value which is positive also and it is negative also. So, you can use the central differencing in this case. and your scheme will still be stable. In fact, you should use central differencing in this particular case. The reason for that is the central differencing is more accurate. So, if you use that scheme FTCS, okay, so your solution will look like this, and your value is basically this is first order accurate in time and second order accurate in space, right. And ultimately, you can write this equation in this form, and here I am defining the diffusion Courant number, okay, which is lambda. Again, I am using the same term lambda nu delta T by del x square. Okay. So, now your diffusion will depend on your delta T, delta x, and what is your diffusion coefficient. Okay. In the fluid dynamics case, this is the with the viscosity. Okay. If you are using the thermal problem, this will be the thermal conductivity K delta T del 2 T by del x square, right. So, this lambda needs to be basically honored even in this case. Okay. So, what is saying it here is, so nu the unit is meter square per second, okay, and delta T is basically second. So, this is basically nu delta T is basically how much area it is covering, okay, at a given time, and delta x square is basically the your grid area in a way. Okay. So, it still has the same meaning that how much it is diffusing in a given time in per unit time should not be basically bigger than your grid size. In fact, the requirement here in this particular case, as we will see later, is basically it should be less than 0.5. So, earlier we had lambda equal to C delta T by del x less than 1, here it is less than 0.5. Okay. So, you can write a pseudo code in MATLAB, okay, like we have done earlier. The initial condition remains the same, the boundary condition remains the same, only the problem has changed, and we want to see that how that square wave is diffusing with time, okay, with a given diffusion coefficient. Okay. So, this is your central differentiating ui plus 1 minus 2 ui plus ui minus 1, okay, and remember this is del T u by del x square, right. So, this will be ui plus 1 minus 2 ui plus ui minus 1 by delta x square. Okay. This is the double derivative, and we had derived in the last class the discretization scheme for the double derivative, right. That is what we have used there, and you can see nu dt u n I plus 1 u n I and u n I minus 1 here by dx square. Okay. So, please go back and write this code in your favorite software or favorite language that you want. Okay. And this is I am showing you some solution. Okay. So, this is your initial condition d equal to 0, okay, and with time. So, our diffusion coefficient here is nu equal to 0.1, your viscosity is 0.1, right, and you can see that it is basically diffusing with time. So, it is not propagating, there is no convection here. Okay, it is staying at the location that we have given in the initial condition, but it is basically diffusing in all the directions, and with time you can say that it has, for example, this is at t equal to 0.5 and it has diffused quite a bit. Okay. Now, we are going very close to basically lambda equal to 0.5, okay, and you can see that to start saying that solution is about to blow up here. Okay. Same scheme, only thing that we have done is that we have increased the value of nu. So, your nu delta T by del x square increased, okay, and it became very close to 0.5, and you can see that it start is about to blow up, and if you go to the next step which is 0.243, and then you can see that it has blown up completely. Okay. So, this is still the FTCS scheme, but my lambda is greater than 0.5. What I want to show you here is that let us say use the negative viscosity, okay, or the negative diffusion coefficient. So, when it is a positive diffusivity, it diffuses basically the magnitude goes down. Okay. When the diffusion is negative, then what will happening if the viscosity is negative, that will basically amplify, okay, amplify the things, and you can see that it quickly amplifies, okay, as soon as you take this nu equal to minus 1 and your solution blows up. Okay. So, that is why the negative viscosity is not allowed. Okay. So, your lambda, I mean what you see is basically lambda mode is still less than 0.5, but the solution blows up because your viscosity is negative. Okay. So, it amplifies the solutions very quickly and it is there everywhere. Okay. So, last thing that we want to discuss is the convection diffusion. So, we have seen the convection. So, this is a convection part and this is your diffusion part. Now, we are combining both of them. Okay. Left hand side is the convection and right hand side is the diffusion. Okay. So, here we will use the forward in time, okay, this is backward in space as we have done earlier, and we are using this central in space, okay, for the diffusion term. So, if you do that you can rewrite it here, okay, in this form. So, if you do that, u I n plus 1 minus u I n by delta t, that is the first term, plus C u I n minus u I minus 1 n by delta x, that is your second term, is equal to nu u I plus 1 n minus 2 u I n plus u I minus 1 n by delta x square, okay, that is your third term. And you reorganize it, this equation, and you get this in terms of n plus 1. Remember, always you try to keep your n plus 1 on the left hand side and all the things which are known at the given time are on the right hand side, and from the right hand side you calculate the left hand side. Okay. And here you can see there are two Courant numbers. Okay. So, one is lambda c and other is lambda d. Okay. So, usually the diffusion Courant number is not that restrictive. Okay. Typically what you need to worry about is the convective Courant number, okay, because that value is usually lower than your diffusion Courant number. Okay. So, let us look at the problem. So, we are using the same thing, C is equal to 0.5 that we have done for the linear convection, nu equal to 1. Okay. So, we have seen the solution at purely convection and purely diffusion for this case, and this is my n x is equal to 51, x max is equal to I think 2, okay, and T max is equal to 0.5 and n t equal to 151. Okay. So, you get these values, and we have done separately, we have seen the behavior for the linear convection and the diffusion. Here you can see, because there is both the convection and the diffusion, because of the convection it is going right, the convection speed is positive 0.5, and because it is the diffusion it is damping down quite a bit. Okay. Even if you recall, when we discussed the linear convection, there also it was diffusing, not this much, but there also it was diffusing slightly when we are using, for example, the coarse grid. Okay. Why that was diffusing there? In that particular case we did not have the viscous term, but the diffusing because of the something called numerical diffusion. So, although we are not putting any diffusion from our side, there is still some diffusion in the numerical scheme itself, because of the choice of a numerical scheme it is getting diffused. Okay. So, here it is both the numerical diffusion as well as the viscous diffusion, and that is why the diffusion is faster. So, you can see the convection on the right hand side and diffusion as the magnitude goes down. Okay. The last thing that I want to discuss today is the Burger's equation. So, this is basically a non-linear convection diffusion equation, okay, and it is a very famous equation. If you have a new scheme that you want to test for non-linearity, before you go to the solving Navier-Stokes equations, this is the very good scheme to test, because it has got everything that you see in the Navier-Stokes equation. You have the time derivative term, you have the convection term, and you have the diffusion term, and you also have the non-linearity, right. So, same approach that you have to use like we have done earlier, forward in time, backward in space, and central in space for the diffusion term, and this is how your scheme will look like. Okay. And you can solve the Burger's equation for the problem that we have discussed earlier, but I am going to show you solution match with a theoretical solution. So, for certain conditions and certain transformations, you can basically transform this equation into a kind of heat equation. Okay. And because you know the heat equation is solvable directly theoretically. So, you can get the solution for the heat equation, and you can compare the numerical solution with the theoretical solution. So, that is what I am going to do today. So, you can write this equation. So, you can take this all the del by del x term on the right hand side, that will become u del u by del x minus u del by del x plus nu del t u by del x square, and this can be further written as del u square by 2 x plus nu del t u by del x square, okay, and that you can write as del by del x nu del u by del x minus u square by 2, right. So, you can cast your Burger's equation like this, okay, and then we will use something called Kohl-Hopf transformation. So, why you are using this transformation? Because you want to get the theoretical solution, okay, for this problem, and it is possible to do that under certain conditions, okay. So, this is very close to like you recall in your calculus, you basically change your variable. So, you will do the variable transformation and you convert your PD into ODE in many cases, right. So, this is very similar to that, okay. So, the form that is suggested is u equal to minus 2 nu by phi del phi by del x, okay, and if you put this value of u into this equation, let us say A, and you basically simplify it, you will quickly see that you will start looking at like a heat conduction equation, okay. So, you have this del by del x term both the sides, and the solution of that will be phi t is equal to nu phi x x, and plus you can have some function, okay. You can again use another transformation, and you can write it completely in the form of heat equation. I will not go into the details, okay. You can look at it in any textbook, and let us say this is your you use the periodic boundary condition, okay. So, your final equation will look like this, use the form of u which is shown here, okay, and the phi form is given here, and you can get, for these two conditions you can get your analytical solution. So, the analytical solution with time will look like this, okay. You can see the time term is there, okay, for a boundary which is between 0 to 2 pi, okay, and you have this analytical solution given, and u function is defined here, right. So, I will show you the solution between the analytical solution and the numerical solution for this problem. So, I have taken nu is equal to 0.1, okay, it is a coarse mesh, Dx equal to 1257 and dt is basically 0.0033, and what you see here the lines are basically the analytical solution, okay. So, you can see that the magnitude is going down in this direction, okay, that is because of the diffusion, okay, and remember this is an analytical solution. So, there is no numerical diffusion here, and it is convecting on the right, that is because of the convection, right. But if you compare that with the numerical solution which are shown in the circles, right, you can see that okay, for the first time if you see t equal to 0.1. So, your analytical solution is the line here, and your numerical solution is actually towards the discontinuity, it is very different, okay. So, this is the line that you are getting, right, and as you go ahead in time, okay, there is lot of diffusion here, okay. Here you can see this is the peak in the analytical solution, and this is the peak that you are getting in the numerical solution, and similar behavior you would see and downstream also here, okay. If you improve the grid size, okay, make it more finer, it will become better, but regardless of that you will have certain numerical diffusion that you cannot avoid, okay. So, in the next classes we will look at the schemes when it becomes stable, what are the criteria where we can ascertain that the scheme will be stable, what are the conditions, okay, and also we will look at some more schemes, okay. So, we have only seen some very simple schemes which are basically FTFS, FTCS, FTBS and so on and so forth. We can also have basically the implicit schemes where you will use. So, right now we are using del u by del t plus c del u by del x, for example, equal to 0. So, here for u del u by del x you are using u I n minus u I minus 1 n by delta x. You can also do an implicit scheme where you will see this u I n plus 1. Your solution that you want to get is also defined at this current time. Okay. So, this will be basically u I u I n plus 1 minus u I n by delta t is equal to 0. So, you can see that here also on the right hand side also this is at n plus 1 and this is also n plus 1. So, these things will come on the left hand side and it will form a, it will give you an implicit form of equations. You have to basically solve a matrix like we have done for the compact schemes, okay. But there are certain advantages of this kind of schemes. It basically allows you to use a higher Courant number, okay. So, we will look at some of these schemes, and after we take a look at these schemes also, we will go to the studying the stability of these different schemes, okay. So, with that we will stop here today. Thank you very much.